We just want to search a really, really big number of them. And then we want to format string. So as some of you probably already know, in C, for all of our string-related functions, we use format strings. And the way that works is that we have a input string, and then we substitute variables into it, which are all represented by the little format specifiers inside of the string, which are referenced here in the table. Now, this uses an interesting C construct called variable arguments. And so one argument is specified here, and it can't point at the screen with my finger because you can't see it, here. And these arguments here are variable arguments. And so what happens is when C parses this string, every time it sees one of these format specifiers, it goes to the end of the string into the list of arguments and goes, okay, I need the next one along, and then this one will go, I need the next one along, and I need to fill it in here. And so what this actually looks like on the stack is we've got our string here, and then we've got our name, a string, to point it to where the string starts, and then we've got our age, and then we've got our return address, and we've got our local variables from the function that called it, and so forth. Now, the problem with this is that if we don't specify these arguments in the variable arguments list, when the string goes to, when C goes to pull out the next item in the list here, it is going to look at the stack, and it is going to look at the next thing on the stack, even if there's nothing there, and it's going to print it out. So we have an example of that. And I think I called it format example C, yes. And not that one. Beautiful. So if we use this piece of software here, what this is meant to do is it's asking you to input your parameters, and it will then input a string, and it will just print it back out to you. So if we say hello, it'll just print hello back to you. But you notice here inside of the printf here that what we're using is not a string formatted like this and inserting the parameters in. We're actually just stuck it in here. So C will treat it as though it's got format specifiers in it. So the danger is if we go to use format specifiers inside of our string, it will actually print off other things down on the stack. So the example here on the stack in reverse order, because remember the stack is built up in reverse order, we have C, B, A, and if we look down here, we've actually printed those off the stack. CBA. So in here we'll have our return address. And so as a result, what we've actually done is we've leaked memory. Now this is horrible. You might think, it's a little memory leak, who cares? Heartbleed was a little memory leak. So moving on, right? Wouldn't it be so much cooler if we could actually write to that memory? Not only could we leak that out and use that to discover things on the stack. So we could have a variable further up with a special password that we needed, and we could leak that out. But what if we actually wanted to modify what is in memory? Well, that is what this lovely N format specifier is for. So if we go back to the start to our table, what N does, N stores at its associated position on the stack, it stores the number of characters printed so far. So if we go to what the stack would look like, let's say that this was not %s, but it was %n. So as a result, treating this value here as a pointer, we would then write into that address 1, 2, 3, 4, 5, 6. So as you can see here, %n, the number of characters that are printed so far in this whole string is stored at the address Charles printed. Now, also one little addition before we continue that I want to mention is the use of the $sign operator. The $sign operator lets us reference things later on in the stack. So if we put $3 $3 we would be trying to represent the third integer on the stack. That's important later on because that's going to actually let us skip along the stack. Because remember that when we're doing our exploit, such as here, we've only got 10 characters. I can't print any more than, you know, %x 10 times and leak 10 hexadecimal values off the stack. I can't leak more than 10 of those with %x in a row. But if I want to reference something later on down the stack, this lets me do it. This is even more important because we will end up copying this. We will end up copying this string to the stack here for user input, and so we will end up actually chasing ourselves. And so what that means is that if I put %p, 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 we would actually see in our printout is we would see lots of %p's and only a little bit left over at the end. So I'll demonstrate how we can get around that now. So here is a terribly written C program that I have just realized I haven't even freed this yet, but we'll just ignore that. We haven't even freed the memory that we put on the heap. But if we run it, what we're supposed to do is input a string. So if we write hello, it is going to say, no, that's wrong. But if we put in our magic string, it is going to say that was correct and it's going to give us a shell. So it's like a fake little pseudo program to open a shell. Righto. So what we can do with this is, why don't we try and come here and look at this. Now, what we're looking for is that there's a value in compare. So when compare is greater than 0, this if statement is going to result in true. So if it's anything besides 0. So what we want to do is we want to write another value into compare, but we can't directly write another value into compare. But then notice we've got this lovely print statement right here. And this lovely print statement is above on the stack the compare pointer. So wouldn't it be nice if we could reference this, reference the compare pointer from our printf using a exploit, using a string format exploit, and as a result, add something to compare, and then make compare something other than 0, and then this if statement will run. So let's have an example of that. So the first thing that I am going to do is pretend I'm not looking at my notes and pray to the demo gods that this works in real time. So let's open our software. So let's make this full screen. So the best place to set a breakpoint would probably be at the print statement that we're going to deal with, because we want to inspect what's going on and we want to have a look at memory. So let's put a breakpoint here at 20. Righto. Now let's try and see what memory looks like when we add something into it to get an idea of where things are, and we'll then find where this compare pointer is and figure out how to override it. So if we run this with the value of AAAA, righto, we're going to now hit our breakpoint. So we've now run down to here. So as a result, we've done our comparison. It's going to come out as false. What we can do is we can now reference memory. So let's write out 48 words in hexadecimal from the stack pointer. Now I'm just thinking for a minute. Did I disable ASLR? Just let me quietly do that on another monitor. We can have a look here. So I stuck in these lovely little flags here for us to find. There's a hard BBBB, which is these 4 2s here in memory, because that is the ASCII code for B. And there are these 41414141. Now this here represents our 4 capital A's. So these are two lovely ways to find out where the edge of our stack is. Now, what we want to do is we want to find out where compare is relative to all of these. Now, it's no accident that I've used a pointer to compare, that I haven't just passed compare back and kept it as a local variable. And the reason is just to simplify things for the demo. Because if we go back to our table of format specifiers here, n is supposed to be a %n is supposed to represent a pointer, an integer pointer. So that is why we've cheated a little bit to make the demo a little bit easier to understand. So we need to find where compare is in this whole mess. So what we can do is we can print the address of compare. Now compare FFFCB2C, which will be CB2C. It should be here, but just to double check, see what it should have in it, and it should have, that is correct. Beautiful. Now if we count this up for so that means that we should have a gap of 28. Right, so you would think that we want to jump to 28 indices from the start, but that is not quite correct, because if we quit GDB for a minute and we run our string application, we can see here that there is in fact, let me put some spaces in it so it's a bit easier to read. We can see that we have 3 more addresses here that start before this 42. So our offset is not 28, it is actually 31. So what we know is that if we were to go back into GDB for a moment, and we were then set our breakpoint at 20 again, and we would then run with the value of AAAA, and then we would put %31, because we want to put a 31 offset using the offset operator that we discussed before, and we want to print memory 31 from the start, from the top of the stack at the point. What we should see is, oh wow, that's our address. That's the pointer that we identified before that holds compare. That holds right here. That's what we want to change. Now, all we have to do now is we have to write that. We've identified it. And so if we change P to N, what we're going to do is we're going to write how many we've printed so far, so AAAA, to a value 31 from the top of the stack. And even if we write 4, the value of compare, because we're printing 4 characters, the value of compare is going to be greater than 0. And as a result, with a if statement, any value greater than 0 equates to true. And so in theory, it should allow us to proceed. So if we put an N there, ta-da, we have a shell. It worked. And just to confirm that we're not crazy, we can run it. We can run it with anything. We can run it with a single A. Anything that's non-zero should work. So we should then go %31 $N. And it didn't work because it's live on camera. And it worked. There we go. Beautiful. So as a result, what we've actually done is we'll do a recap. Our stack looks like it's got the format string of what we've typed in on the top of it. And then it's got our whole array. Then it's got our flags. Then it's got other stuff on it. And then it's got our compare at the bottom. Now we've figured out that our compare is 31 down from the top of the stack. And what we're doing is we're writing how many characters printed, a value, into that value 31 from the top of the stack. And so as a result, we're changing compare. And so we've now been, with a format string exploit, we've now been able to modify a variable on the stack and change the control flow of our software. And so we did not need to know the value of our magic string. And so that's
Hang on.
Yes.
We can ask questions, by the way,
Yes.
guys, if you're interested. I'm going to ask, why did you need to put like single quotes around like the 8% $31
I'm pretty sure that's got to do with formatting from standard input on Bash, because otherwise it is going to interpret those as not a string. It's going to try and do its own pre-formatting mumbo jumbo on it, and that's why it wasn't transferring it across properly. I'm 99% sure, because sometimes you will notice when you do an exploit, if you do not wrap it like that, and you go to print it, so even if you were to cat it out, it would actually look slightly different. And so this is making sure that we're passing it as is to the exploit. Does that make sense?
Yep, thank you.
No worries. Any other questions before I continue? No, alrighty, cool. And the next thing I'm going to talk about is memory protections, how memory protections work and how to bypass them and deal with them on modern machines. So as you would have noticed when we've gone to compile stuff, our compile strings for all of our exploits look crazy long, right? You know, we've got our output that we're creating, we've got our C file that we're compiling, and then we've got magic value that we never really considered, another magic value that we never really considered. We have our 32-bit, this means GDB, and this is what I put in because this can remove compiler optimization and sometimes make it, when you're looking at the disassembled code, it looks a bit easier because compiler optimization hasn't happened. Now, what all of this does is prevent some of our exploits from working. That's why we need to use them. Another one that we always enable is we normally run something like this, which disables ASLR in the Linux kernel. So we're going to look at how all of these memory protection mechanisms work and how to defeat them. So the first important one is executable space protection. So you would otherwise know that as NX bit, and we enable that in GCC with the -z exestack command. So what this does is if you imagine you've got memory and you've got different pages in memory, what we're actually doing is we're saying, hey, you're not allowed to treat certain ones of those pages as though the code in them is executable. And this prevents, that means that we can say, okay, so only someone trusted has got access to executable pages. So anybody can't come in and inject shellcode in and redirect control flow and execute their shellcode. It prevents that from happening. This is not a new idea. The 80286 from 1982, I think it was like Intel's second mainstream processor or something, had segment level protection in it, but not per page level. Per page level was done in the more recent AMD 64 ISA. It's very, very embarrassing when your competitor writes the new ISA Intel AMD. Never mind. But sorry?
Can I add something?
Yes. So
while the NX bit has been a feature of processors for a very, very long time, the first time it was actually implemented in an operating system was 2003 in OpenBSD.
Yes.
And then Microsoft introduced stuff like DEP in Windows XP in 2004. So it's pretty old. It's a pretty old exploit, but yeah.
And I believe PAX, the PAX guys were the first to introduce it in the Linux kernel. I'm pretty sure as well. But yeah, it's a pretty old, but the idea has gone back a very long time. So just a small aside, has anybody here ever used an Arduino or use an Atmel AVR microcontroller at all? So anybody ever heard of Arduino? Alrighty. So Arduino is a small little board that people plug things in and program to do real world stuff. That's using a different architecture called a modified Harvard architecture. Now, that follows the idea of a separation between program code and the stack. So basically we can't have the code that is executed and the code that is operated upon and the memory that is operated upon is in different areas and they can't intermingle. That's sort of not what we're going for in modern machines with von Neumann architecture. And so we need that for things like JIT. So if you've got JavaScript with a JIT interpreter, you need to have an executable stack, because we need to be able to write executable code in real time on the stack and then direct execution and execute it. So we can't completely disable this. That's why we need it for some things. But the reason we need this ZXE stack is because we don't enable it by default. Now, obviously what this means is that if I introduce some shellcode onto the stack, and then I, do a standard shellcode attack, and I redirect control flow to it by, changing the return pointer, and nothing's going to happen, because the operating system is going to go, that page is marked as non-executable, I ain't executing there. So how do we get around that? Well, let's try and point to some code that's in executable portion. It's in a portion of memory where the page is allowed to be executed, and let's reuse what we already have. So hence a return to LibC attack. So LibC is a section of libraries in the computer that contain object files of compiled functions. So basically what happens in your machine is that when you write a software and you import libraries, you don't import all of that software compiled into your binary, because then your little binary that does one thing will be really, 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 really massive. Sometimes we have to do that, and it's called static linking. What we actually do is we have one set of these libraries on the entire machine. And what we do at runtime is we dynamically link to them, and we say, the offset table has told me that my printf is over here at this portion in memory. And so we then go look up that portion in memory, and we make a little function pointer to it, and we set up the stack for it like this. We put the address of the function we want to call inside of libc, and we put the address of where we want to go after it's done, which is the next portion in our code that we want to continue addressing. And then we put all of our parameters on it, and then we call it using the x86 call instruction, and then the magic happens. But the beauty is that section of memory always has to be executable, because we're going to use it at other portions inside of our application. So what a return to libc attack does is we're going to go in and manipulate our stack and our return instruction to actually point to one of those functions that we want to use inside of libc. So a very common one is system. System is a call that lets you open a application on the call any application basically on the machine that you can provide a path to it, and it will execute it. So what we can do is we can go find where that is inside of libc, and we can whack its address on the stack up the top here. Then we put where we want control to resume when that system call returns. We'll just leave it as 0, because we don't care. If we're going to have it execute a shell for us, which as you can see here, the parameter of what we want it to execute is sh, it doesn't really worry us if it crashes when we're done. So we'll be really lazy about it and leave that as 0. And so as a result, we can make a return to libc attack. And so here is an example piece of code, another poorly written example piece of code. So what we're trying to do here is we're opening a file, and we're reading from the file, and we're putting it into a buffer in memory, and we're printing out what you've read. So it's basically like cat does on Linux, where we write cat.retc, and it prints it out to screen. So if we go retc, it ignore the segmentation fault, it will does the same thing, prints it out to the screen. Now, if we want to exploit this in order to use it as an entry point to start a shell, what we can do is we can actually exploit what's put into the buffer and do a standard buffer overflow. But instead, we're going to call a function in libc, we're specifically going to call system. So as you can see here, we have our user buffer, and we are using a non-secured read operation, one that will let us overflow the buffer. So let's continue. So the first thing that we want to do in our investigation is we want to find, and here we are, I have a payload generation application here already. Let's blank this out so we don't give away the answer. But it's structured exactly the same as a shellcode previous shellcode vulnerabilities with regards to finding a return pointer. So I'll skip that for the savings of time because we're running out of time. But basically, I've identified that the return address is 46 bytes from the top of the stack. So hence we're going to pad 45 zeros. Then we're going to add the return address on the stack is going to be the next function that we want to call in libc. So what we're going to do is we're going to search libc in a moment and find the reference to system inside of libc. And then this here would be the return address of what we want to do after we've returned from libc. As I said, we're going to be lazy and just leave it as zeros. And then this here is going to be the parameters that we want to provide to the system call. Now, we'll get onto that in a moment. So the first thing that we probably want to do is find where it is that we're executing. Let's stop here at this printf statement after everything's done. So let's set a breakpoint here. Now, the next thing we probably want to do is find the address of system. Now, since system is in memory, we can just be really lazy. And can I not spell system? Oh, hang on. Is just print literally P system, print where system is in the current memory map. And we can see here that the system in libc, the reference to this call is here. So just a quick aside, the way this works when you normally reference one of these calls is it works like a function pointer. C essentially goes to the offset table, looks it up and goes, okay, the call I want to make in libc is here at this address. And when you write printf, what it's actually doing is it's actually making a call to a function pointer that it's created to that address inside of libc. And so in this case, if we use system, it would be calling this address here. Beautiful. So now what we actually need, we need an address of the string that we're going to provide libc to call. There's multiple ways of putting that in. We could put that in on the stack ourselves, right? So we could put it in above us and put in part of it. Instead of our padding being zeros, we could actually put in a string that we're going to provide system to call for whatever application we want to run, or we could go search it from environmental variables or so forth. But the problem with that is that's all very variable, particularly with other things introduced. The nice thing about our finding things in libc is as libc is randomized once on startup, because that offset table needs to be the same the entire time that we run, because we need to know where to get things from. We need to know where to get these functions from. So anything you get from libc ain't gonna change during that runtime. So we can be really sneaky and go find what we want in libc. Now, banking on there'll be a reference to sh in libc for a couple of reasons. There always is. So let's go see if we can find one. So what we'll do is we'll look at our memory range, memory ranges that are mapped for this application. So what that means is that between these addresses here are all addresses that we can actually access in the memory space of this current application that means something. So as you can see here, LibC starts at this address right here, and LibC ends at this address right here. So if we want to search all of LibC, what we can do is we can find, using GDB's find command, find the start address of LibC, how many bytes we want to search. We just want to search a really, really big number of them. And then we want to look for our string that we're going to find. Let's just find SH. Oh, and we've got a list of them, a huge big list of them. These are how many times SH has been referenced, the string SH has been referenced inside of LibC. So just to confirm that we're not going crazy, we're going to search. So what this means is that we're going to look up memory as though it's a string at this address, a null terminated string. Oh, and we do indeed have SH. This is important because this here is a pointer to SH, and our system call is looking for a pointer to a string of the parameter that we're going to execute. So if we then copy this and dump that here, what we are then going to do is we are then going to add at the return address on our stack. So think of this as a regular shellcode vulnerability, but instead of directing the return address to be towards our shellcode, we are going to point it towards our system call in LibC. Then we're going to add our return address on the stack, and then we're going to add our parameter that we're going to pass the system. So if we go back to our table here, we're set this up on the stack. This is what the stack looks like. So as a result, when the call is finished and the function pops from the stack, and it takes it pops the return address from the stack, throws it into the instruction pointer and goes to execute it, it's going to pull this off. And then it's going to look 2 down on our stack to find our parameter. So let's execute this, shall we? We'll close this, and then we'll go payload. And then what we'll do is we'll run this with the new payload that we created. So this just creates a payload text. Start it from the beginning, ignore that, and there we go. We have a shell. What we have done here is we have completely ignored the fact that our stack is non-executable, and we have done a return to LibC attack. Let's, for the sake of testing our luck, do it outside of GDB. Any questions? Righto, cool. So yeah, just to recap, what we've done is instead of putting our own code onto the stack and redirecting the return pointer to our own code, we've redirected the return pointer to an executable page that was already in memory. So we didn't need to put in our own shellcode. We've actually used what was there already to construct it. Now, if anybody's interested in this, there is an amazing Live Overflow video about this where he talks about return-oriented programming, and basically you can chain a bunch of these together. You know where we ignored our return pointer? What you can do there is you can put another function there and put some more parameters in and actually have it execute a chain of functions. It's pretty cool. Righto, and so the next form of memory that we're going to talk about overcoming is ASLR. So ASLR is address space layout randomization. And so basically what that means is that when the function is started, the addresses that it occupies on the stack. So let's go back to GDB for a minute and I'll give you an example. Break 20. So here is the address that our application lives in memory. Now, if we turn address randomization back on and we actually rerun that and we do the same thing again, it should have changed, but it didn't because it was compiled as pi. But that's anyway. So basically what it does when it's not compiled as a non-supporting pi, because that one was compiled as negative pi, is it changes those addresses here that the function lives in memory. This will be moved around, and that is why when you do your shellcode, the return address can change its position on the stack, and where you jump into the shellcode can change on the stack. It can muck things up greatly. It also randomizes the library locations, so where we pull things out of LibC, but it does those once on startup. Now, all that ASLR does with randomizing the location, it's still relative to each other. So this item is still directly above this item, but they're at a different mailbox in the whole stack. Now, it doesn't mean that it makes it any easier for us to know when an attack has happened as such. And it doesn't stop us from crashing the application, because if we were going to have it write to an illegal portion in memory, we can still do that anyway. That's not very hard. But what it is going to do is stop us from doing perfectly crafted attacks where we need to jump into a known portion of memory. But there is a way of getting around that. So if we then go to our shellcode MOPP example, righto. So basically what we have to do with this function is exactly the same as the previous. We have to redirect code execution, but this time we have an executable stack to open a shell is what our aim of this is. This is the same application as before. It just spits out the application, the file that the user has given it. Now, the way that we're going to do this is with a MOPP sled. So if we open our payload, so the way that a MOPP sled works is a MOPP sled is, or otherwise known as hex 90, is an x86 instruction that means skip, continue on. You know, if you land on me, just go to the next instruction, don't do anything. It's a pretty empty, it's just a test instruction. It means skip, basically. Now, because the address space is randomized and is changing all the time, you know, if I put my shellcode at box 20, you know, address 20 in our stack, well, then the next time it runs, the stack is going to be, the address is going to be different where my application sits in the stack is going to be different. And as a result, if I've referenced with my return address 20 again, it's not going to be in the same place. So we need to make a guess. Now you could sit there and keep rerunning it and rerunning it and rerunning it and rerunning it and rerunning it. And you know what? One day it would work. One day it is truly random. One day you would hit the correct address and it would work, but it would take you an awfully long time. So that is why we use a MOPP sled. And what a MOPP sled means is that we have to just land, our return pointer has to just point to any of the MOPPs inside of our whole MOPP sled, and the shellcode after it will be executed. So if we've got an array and we've put our shellcode at the end and we've got 500 MOPP instructions in front of it, we've actually made our landing strip 500 times bigger. It's like trying to land a 747 on a cattle farm, something the size of a large cattle farm. You know, it's pretty hard to miss. And so what that means is that we should in theory have to do 500 times less tests in order for this to work. So what we do is we try and maximize the size of our MOPP sled. So if we have a look here, we have a 500 character buffer. Lovely. And what we should do is go back to our payload and we measure the size of our shellcode. That's what that is here. And so basically what we're saying is that we're going to do MOPP instructions, or we're going to put our shellcode at the end of the 500 characters, and we're going to do MOPP instructions to every moment before it, and then after it, we're going to just write empty bytes to our return address. The reason why you want to keep your shellcode at least inside of the buffer is because as soon as you even though we're counting and overriding the buffer, some of those addresses can then be changed later on in execution for other various reasons, and we still want our shellcode to be at least intact later on when we jump back to it. It can cause you problems. So that is why I choose to write empty addresses between the end of my buffer and my return address, and I don't actually extend my shellcode out past the end of the buffer, just for that reason, because sometimes it can cause problems. Now, what we need to do now is well, I'll give you a demo. If we open our shell with MOPP and one moment, please. I don't know why the name of it has changed. I obviously changed it. Righto. The perfect point for us to break would be that print instruction again, which is line 39. So let's put a breakpoint there and let's run. Actually, let's remove our, zero this out to not make it too easy. And run our payload generation again and run with. Now, let's inspect what the top of the stack looks like. Let's do 100 words. Now, as you can see here, you can see all of our MOPP instructions. That's not even enough. Well, it's a 500 word buffer, so let's print 600. Righto. So as you can see here, you can see all of our MOPP instructions, and then you've got our shellcode here at the end, and then you've got the return address here, which you can determine. Well, let's determine it. Let's find it. The return address will be that. You find it like a normal buffer overflow. I'm just going to get lazy and find where the offset is. I calculated it before. It's 20 from the end. So if we search for it, it's, what's the address again? 6237. Anyway, it's here somewhere. You'll have to take my word for it. Works just like a regular shellcode vulnerability. We find our return address, and then we're writing over our return address with the start of our shellcode. But a start of our shellcode is here. But we're not going to jump into here. We're happy to jump into any point here, because any point here, the instruction pointer executes 90. It'll go, oh, go to the next one. Execute 90, it'll go, oh, go to the next one. It will do it all the way down to our shellcode. So as a result now, we don't have to find the exact starting address of our shellcode. We can actually just jump in at any point inside of the NOPs, which means that if there's 500 NOPs here, it's 500 times easier to find the address. So let's just pick any address. Let's pick this one right here. And let's then go to our sled address here, put it in, and regenerate our payload. Now let's turn off ASLR for a moment. And as you would expect, it works. Cool, great. Let's turn back on ASLR. And it's going to fail, I know straight away. Oh no, oh no, oh no, oh no, because our memory address has changed. But due to the fact that it is random, one day, this address here is going to line up with the NOP sled. So what we can do is we can run this in a while loop, and eventually it's going to work, hopefully. It will not make a liar out of me. Because what's going to happen is the stack is going to be realigned every single time it's executed, and one day that address that we put in is going to be smack bam in the middle of that NOP sled, and it will work. It just might take some time. Any questions while we wait? Alrighty. There, beautiful. And we have a shell. And what we have done now is we have done our attack with ASLR enabled. So essentially what this tells us is ASLR just makes it harder to pull off the attack. It's not going to stop anyone from doing an attack. ASLR makes it a lot harder to engineer your attack. ASLR makes it a lot harder to pull it off, but it's not really the end all and be all of memory protections. And the final thing that I want to talk about before we run out of time, and I'm really pushing it, is the stack canary. Now, I'm not going to have a demo of this because I believe it could be an entire lecture on itself, how this works. I could spend 2 hours explaining this and making an attack of this, but I will do an overview of how it works. So basically what we have when you compile with the stack protection options, which is enabled by default, that by the way is why we need the F no stack protection to pull off our exploits, is we have a canary. So what a canary is it's a value that we place on the stack just before the return address. And what it does is when we're about to return the function, this canary is taken off the stack and it is actually checked to a value stored elsewhere of what it should be. A simple XOR operation happens. And as we know with XOR, so long as if you XOR two things and they're the same, it's going to come out with all zeros. So if it does an XOR with what it's meant to be, and if the XOR value comes out with anything besides zero, oh, we know the canary's changed. Why is the canary? It's the same. It comes from the adage canary in a coal mine. They're going to be the first to know when something's wrong. You're going to be the first to know when you run out of air in a coal mine, hence we have a canary. It is going to be the first thing overwritten and changed before the return address. Because if we have a buffer over the top here that we are going to overflow and try and write over the return address, we are going to have to write over the canary first. And so as a result, we're going to get a stack smashing warning. We will come back to this in a minute. So an example is, if we do this, yep, we got a stack smashing warning. Cool. So what this is saying is it's check the canary, and the canary is not what it's meant to be. So it's going, oh, somebody's tried to overflow me. Righto. There's another important part of the canary that we will get to in a moment with how one would bypass it. The canary ends with the least significant bits the least significant bytes are null bytes. And the reason we do this is to make it a lot harder to insert, because as you know, a lot of C operations such as strcopy and strncopy both end on a null byte. They do not copy anymore once they see a null byte, and they terminate copying. The reason for this is let's say that you extracted the string canary, which we're going to talk about in a moment. And cool, I've put it in my buffer. I've got my return address here that I'm going to overwrite. That's going to point to my shell code that's in my buffer I just added. And now I'm going to write the canary here. Well, what would happen is you'd write the canary and then you'd stop and you'd never write the return address because strcopy would stop on this. Now, of course, there are plenty of C functions for memory copying that do not stop on a null byte. One of them being gets, one of them being memcopy. There's heaps of them. But this really does shrink down the amount of applications and potential entry points where you can use this to overwrite the return pointer. Now, another really, really, really important thing that's done alongside of this in the same GCC security optimization as the stack canary is applied is the reordering. So if we come here, what this does is GCC realizes that any array that is accessible by a person can be overflowed. So what GCC does is it rearranges it for you on the stack and puts the array at the bottom. So in a normal application, we would look like this. We could overflow arrays, we could write to vars, and we could influence vars and change our control flow, or we could write over our return address. In this one, we put the array under vars. So in other words, it is below it on the stack. Vars is above it on the stack. And so as a result, when we override array, we're actually writing into canary. We're not overriding. We can't therefore change the value of vars on the stack. So as a result, it also, the same optimization, the same function that adds the canary also does this, and it prevents major buffer overflows. Now, how can we overcome the stack canary? Well, there are two major ways of doing it. The first is we leak it. We spoke about leaking arbitrary memory at the start of my incredibly boring long lecture, and that was with a format string vulnerability. So that is one way that if we could, we figured out where the canary is in memory, it should be just before the return address, we leak that value out, and boom, we've got our canary, we'll whack that in and we'll change it. Now, one important thing to remember is that all forked child processes have the same canary, because a canary is created at initial runtime of the application. And the way that a fork system call works is it copies the entire stack, copies the entire application, basically makes a duplicate of it and lets it continue running. That's how the fork system call works. Now, since the canaries are created at the start of runtime of that application, what we can do is we can test on, if you have a way of forking a process, one process forks many times, you can test the canary change on one fork. No, it didn't work. Test it on another fork. No, it didn't work. And so as a result, we can actually brute force it. So if we try and brute force the value of the canary one byte at a time, and we have a way of overriding memory and overriding it one byte at a time, we just make many forks of the same process, overwrite the canary in one at a time until it works, and we go, oh, okay, so that byte is correct. Let's move on to the next byte, and we do the same thing again with the fork processes, and we use them almost as an oracle to come up with what our stack canary is. Are there any questions? Righto. So I guess this has all been coming down to one major important thing, and that is the compiler ain't going to save you if you write shit code. And so if you can't write secure code and you introduce vulnerabilities and you ignore the warnings from your compiler, because your compiler is going to tell you that you've done something wrong. So if we go, for example, to our format one, and we do this, look at this. We've got a lovely warning: format, not a string literal, and not a format arguments. So this is basically GCC saying, you're wrong, don't do that. If you write poor, terrible code and you manage to ignore your compiler, there really is nothing that is going to save you. These things are going to help and these things are going to try and mitigate the damage, but the onus is still on the engineer that writes the code to be security conscious, and that is important. Yeah. I believe that is everything. Are there any questions? Righto. Thank you very much.